All right. How y'all doing? My name is Gabe O'Regan. I am the Group 4 reporter, reporting on last week's lab, Lab 5, the Rankine cycle. Quick introduction, just to remind y'all. So the Rankine cycle is a thermodynamic cycle used in power generation systems. It involves converting heat energy from the boiler into mechanical work via the turbine. To explain the figure on the right, 1, 2 is our compression cycle. Water is pumped back into the boiler. 2 to 3, the boiler heat addition. Water is heated to form steam. 3 to 4 is our turbine, our extracting work. Steam expands and produces mechanical work. Finally, 4 to 1 is our condenser, where we're rejecting the heat. Steam is condensed back into water. Continuing on, just a quick look at our experiment goals and our data collection, what we're really trying to get out of this experiment. So our primary goal was overall to understand the Rankine cycle, but we're also trying to measure data such as pressure, temperature, and our power output. By collecting this data, we'll calculate key parameters, efficiency, and the effect of loading conditions, which we'll see later on. Moving on to our experiment results. First up was our fuel flow versus time. See the plot on the right, there's a big green square there. That's just a visual of our steady state window. I keep the steady state window steady for all of our plots. I'm starting at 2 minutes to 7 minutes. I was also required to find an analysis point, which would be the basis of, the constant time of where I'm finding each respective value. So for example, for fuel flow, the fuel flow at that time was 4.49 liters per minute. Moving on again, boiler temperature at that analysis point, 173 degrees Celsius. Boiler pressure, 106 pressure, gauge pressure. Later on, I converted gauge pressure into MPa, so it was easier to use the tables, the steam tables. The inlet and outlet turbine pressure at our analysis point, we had 13.265 and 3.31 gauge pressure. The inlet and outlet turbine temperature, 117 degrees and 104 degrees. Our current that the generator was outputting at our analysis point, we were getting about 0.496, and that's what we were expecting to get. And same with the voltage output. We were trying to stay around 9 volts for a steady state value. 8.3 is pretty good. And lastly, our turbine speed. We had a value, 2,500 RPM. We had to stay below, so the steady state speed of 2,071 RPM is pretty good. Here's a summary of all the values I just spat out. I also included the fill amount, the initial boiler fill amount, and the water used. Those were found by taking, you had the fill glass, and you would take the difference before and after the experiment, and there was a conversion table in the lab manual that I used. Let's move on to sample calc. So this is where I kind of got a little weird. So when I was calculating the mass flow rate to help calculate everything else you're about to see, I was getting a really small mass flow rate. And I did it with the boil water usage, so the water that we're using throughout the experiment. I just could not figure out why this was so small, but I just kept with it. Moving on to our heat flow from the boiler, we're getting 10.3 kilojoules per second, which is a lot lower than it should be. The work rate in the turbine, again, super small number, 0.0837 kilojoules per second, and then our generator efficiency, pretty garbage, 4.9%. Our heat flow from the condenser, this was a little bit better. or heat from the condenser, 9.97 kilojoules per second, and their efficiency for the condenser, 96%. Now this is the steam table properties from all 5 of our systems, interpolating all of the temperatures, pressure, having our pressure and temperature, interpolating volume, enthalpy, internal energy, and entropy. Then from that, I was able to calculate the whole of the efficiency, thermal efficiency. Again, really low number, 3.82%. This is where I compared the theoretical and experimental results using Hayden's results from 2 weeks ago when he did his lead presentation. Again, these error differences are huge. I'm thinking most of the source of error is coming from the ideal assumption, which I didn't make. There was also some weird, I'm guessing heat losses from the boiler. There was some stuff that wasn't making thermo sense. But moving on, just talking about the effect of loading conditions. Increasing load, more power demand increases the steam flow, is going to raise the pressure and temperature for the boiler, improving the turbine efficiency. We decrease the load, less power demand lowers the steam flow, reducing pressure and temperature and lowering the cycle efficiency. You also have a part load condition. So if we operate below the optimal load, it increases the system's inefficiencies, reducing overall performance and steam quality. And then lastly, overloading, which is our excessive demand that can drop the boiler pressure, stress the turbine, and degrade performance. And lastly, my references. Is there any questions?